Hi everybody. So this is the first of hopefully 3 fairly short lectures or presentations about some concepts that I wanted to introduce in order to just kind of wrap up the semester in a nice way. So this one is particularly important because there is a question on the final exam that you're currently working on that relates to it. And so what I'm going to try to do is kind of explain what the situation means and then give you some ideas of how to attack that problem. So first of all, everything that we're going to talk about here is only an exercise in terminology. You know all of the theory already. You've seen it several times. You've solved problems about it. So you're going to be very, very comfortable with the question as long as you can sort out what the words in the question actually mean. And so the first one, or the first term, is recursively enumerable. So what these terms, recursively enumerable and recursive, mean is they're basically language families. They are terms for languages that are based on a Turing machine's ability to either accept or decide that language. And so a language is called recursively enumerable if there is an acceptor, so a Turing machine that can accept a string that is in the language but does not necessarily tell you or reject a string that is not in the language. So a recursively enumerable language has a Turing machine that accepts it, but that Turing machine could potentially loop for forever for a string that is not in the language. On the flip side, a language is called recursive if there's a Turing machine that meets 2 criteria. A, it has to accept the language, and B, it has to halt on any string that you give it. So one such type of machine is called a decider, and we've already kind of talked about this in a previous lecture. But what a decider does is this thing has to halt such that it clearly accepts or rejects a string. So if you're currently working on the programming assignment version of the final, this is effectively your task. You are supposed to be coding a decider for those 2 specific languages. So what I want to be clear about, though, is that there is some nuance here. Just like standard Turing machines, just like a lot of the different definitions in the course, there are resources out there that have a slightly different definition of recursive. And so our definition says that the Turing machine has to accept and it has to halt on all possible strings, but it does not specify that it has to reject. So the nuance here is that you could potentially have a Turing machine that is not a decider. That is, it halts on an undetermined state. It's not an accepting state. It's not a rejecting state. And that would be a recursive language, even though it's not necessarily a decider. It's some slightly larger abstraction of a decider. That's kind of neither here nor there, but if you see other definitions on the internet, if you're searching around for resources, I just wanted to be very clear that is a bit of nuance that does exist. So the obvious question that comes up in this class all over the place is how can we tie this sort of theory to something practical? So in a practical sense, what is the better scenario? Is having a recursively enumerable computation or having a recursive computation better? And so if you think about sitting around somewhere waiting for a compilation to happen or waiting for a database query to complete, you could have a situation where it never completes. So if your computation is on a recursively enumerable language, then it will potentially go on for forever if the Turing machine does not accept whatever the input is. However, if it's a recursive computation or a computation or a recursive language, then it's guaranteed to complete. And so even though it may take 100 years or 150 years or 45 minutes, you know that it's going to eventually give you an answer. And I don't know about you, but personally, I would prefer the promise of an answer, even if it's going to take me a really long time to get there. And so from an algorithmic perspective, from a building a machine perspective, if you have an algorithm that is implemented by a decider versus an acceptor, that's a much better situation for somebody who's actually trying to run the machine or use the algorithm. So how do we show mathematically that something is either recursive or recursively enumerable? We do exactly what we've done in the previous lectures for the previous language families, and if we want to show that it's recursively enumerable, all we have to do is build an acceptor. Likewise, if we want to show that something is recursive, all we have to do is build a decider. And so going back to our nuance, it's actually a little bit easier to show than building a decider, but if you build a decider, you have obviously shown that it is a recursive language. You've effectively done the harder case. So it also is true that if you want to show that something is recursively enumerable, you can show that it is recursive, because all recursive things are recursively enumerable, but the vice versa, or the contrapositive, is not necessarily the case. So if you remember how we did things like showing that a set of regular languages is closed under some operation, we could basically just build a DFA or an NFA that implements that operation. And so because we know that a DFA or an NFA accepts all regular languages are accepted by a DFA or an NFA, and we could represent that operation by a DFA or an NFA, we know that that operation results in a language that is regular. We're going to do exactly the same thing, except instead of using a DFA or an NFA, we're going to use a Turing machine, and that's really it. So one example is the question, are recursively enumerable languages closed under complementation? So what this means is if I have a recursively enumerable language and I take the complement, is the complement also recursively enumerable? No. And the formal proof of this is available in the text for theorem 11.3, but I don't want to necessarily bog you down and sort of like beat the theory to death mathematically. What I want to do is think about it at a very high level. So if I have L, and L is a recursively enumerable language, what that means by definition is that I have some Turing machine called M that is an acceptor for that language. So if we kind of try to seek out a contradiction, we can assume that the complement of L is also recursively enumerable. And so if this answer to this question was yes, this would be true. And so if the complement of L is recursively enumerable, we know that there is some other Turing machine called M prime, and M prime acts as an acceptor for L complement. But if we have an acceptor for both L and L complement, we can combine them together like we did in the previous lecture to derive a decider for L. So if I have a decider for L, what actually happens is we've shown that L is actually recursive, not just recursively enumerable. And so if that's true for all L, that means that we have shown that the set of recursively enumerable languages and the set of recursive languages are the same. However, this can't be true because we know that the halting problem exists. And the basically bottom line of the halting problem is that there are recursively enumerable languages that are not recursive. And so because these languages exist, we know that the set of recursively enumerable and recursive languages cannot be identical. On the other side, can we show that recursive languages are closed under a complementation? So instead of having recursively enumerable languages, if I take the complement of a recursive language, can I show that there is a decider for that complement? Yes, I absolutely can. And so if I consider a recursive language L, any L, we know that there exists not only an acceptor, but also a decider for L, and we're just going to call it M. So the decider, by definition, is going to solve the membership question. So going back to the programming assignment that can replace your final, basically what you're trying to do is you're trying to build a decider. You're building a machine that says, yes, this string is in the language, or no, this string is not in the language. So this thing is capable of either rejecting or accepting a string in a finite number of steps, even if that number of steps is really, really high. So we have a situation where the decider for M prime just accepts when the original decider rejects. And so this is very, very similar to what we were able to do with DFAs and NFAs. We effectively can just flip the accepting and the rejecting state. We can do some minor modifications of the control unit, and then we're done. So while recursive languages are closed under complementation, recursively enumerable languages are not. And the reason is because of the definition of what a decider is versus what the definition of an acceptor is. So we want to kind of break this down very concretely for what you have to do on the final exam. So on the final exam, what you have to figure out is you have to figure out if the intersection or the union of recursively enumerable languages are closed. And what that actually means, sort of boiled down to English, is can you build an acceptor that accepts both of two acceptors when they accept? So what you're trying to do is you're trying to say, I have an acceptor for a language L1, I have an acceptor for a language L2. Can I build an acceptor out of those other acceptors that only accepts if both of those original acceptors accept? So that is basically your tongue twister for the semester, but that's all you have to do. The slightly easier side of that is trying to figure out union. And in that case, all you have to do is build an acceptor that accepts when either of those two original acceptors accepts. So the union acceptor would accept if L1's acceptor or if L2's acceptor accepts. And that's really all you need. So if you have questions, comments, concerns about the final exam, specifically around this question, please let me know. I'm happy to walk you through it a little bit more. But basically, recursive and recursively enumerable languages are the same thing that we've been doing with acceptors and deciders. We're just calling them weird names because we needed names for the language families. So thanks a lot for watching, and I hope that you're doing well.